Right? Any questions? Any other questions? Okay, so in the last class, we saw this max flow problem, right? It was a network problem where given a communication network and two nodes, one which we call the source and the other which we call a sink, we want to find what is the maximum sort of packets that you can send per unit time from the source to the sink. And we could formulate this as a linear programming problem, and we saw how to solve this, right? So in this class, we'll see another example, but before that, right? But before that, let's look at our constraints. So remember that in the max flow problem, the constraint set was essentially a polytope, right? It's a bunch of linear constraints. So each linear constraint effectively defines a half space, and the intersection of half space gives this at least a polyhedral region. Now, there are, in general, given any convex set, there are two different ways of looking at it. And this is particularly important when you design algorithms, at least how many practical algorithms are designed to solve general convex optimization problems. So one way is exactly as you think of as a polytope. Right? What is a polytope? It's an intersection of half spaces. And in fact, a very nice property is that any closed convex set can be represented as an intersection of half spaces. Now, not necessarily finitely many half spaces. If you take finitely many half spaces, then the intersection gives you a polytope, right? But given any convex set, no matter how complicated it is, as long as it's closed, you can always write it as an intersection, possibly an infinite intersection of half spaces, right? So, for example, let's take a circle, right? How would one possibly write this as an intersection of half spaces? Correct? Yeah, exactly. So you look at all possible tangents to this particular set. You take any point, take the tangent. Now this tangent is basically a hyperplane, right? And all of the circle lies on one side of the hyperplane. Right? Now you take. So this is one particular tangent. Take any other point, take the tangent, right? And so on and so forth. Correct? So formally speaking, one can look at it in the following way. So any convex set C can be written as the intersection of all possible half spaces H which contain the set. So given any convex set, you can look at all possible half spaces which contain this particular convex set. Okay, it's a complicated looking object, right? And it's not at all clear that this should, for example, generate the convex set. Okay, I'm not going to prove this, but this is a fact. At least at this point, I'm not going to prove it, but it's useful to keep this in the back of the mind. Okay. So in particular, if you take the intersection of all half spaces that contain C, you can generate closed and convex sets. This, for example, such an intersection cannot generate an open convex set. Right? So any closed convex set can be written as an intersection of infinitely many half spaces. That's one way of looking at it. If you take finitely many half spaces, then the intersection will be a polytope. Right? But that's how we defined a polytope, as an intersection of finitely many half spaces. Now there's a different way of looking at a convex set, and it is as the convex hull of some other set. Right? So for example, this circle that I have over here, I could think of this as an intersection of infinitely many half spaces. Basically, each half space is generated by one of the tangents to the circle. Another way is I could treat this circular region as the convex hull of basically the boundary, right? So if I take the boundary of this circle and look at the convex hull, what would I get? The entire closed circular region, right? So this is what is sometimes called the half space description of a convex set. And you can also write C as the convex hull of some other set, maybe the boundary points. Whatever is easy to describe. And the description can sometimes be easier in one form and more complicated in another, or it could be easier in the other form. So this is called the convex hull right?
So
yeah.
Second one is also for fully closed.
It's for closed convex sets. For example, you take the open circle. Can you write this as the convex hull of any set? Not really. Right? You can't generate it as a convex hull. So we are only focused on closed convex sets. All right. So, and that is particularly helpful when you look at polytopes. Now, what is a polytope? At least in 2 dimensions, it's just a polygon, right? A closed polygon. Now, once again, there are 2 different ways of looking at this. One is you can generate this as the convex hull of just the vertices, right? Because from the vertices, you can generate the edges using convex combinations of pairs of vertices, pairs of adjacent vertices, and every point in the interior can be written as a convex combination of the vertices. Correct? So that would be the convex hull description of the polytope. Right, so polytope is basically just the convex hull of finitely many points, basically the vertices. Correct? But at the same time, you can also represent it using the faces, right? So each face basically determines one hyperplane. And corresponding to each hyperplane, you have a half space. Right, so you can view this polygonal region either as a convex combination of the vertices or the intersection of these 5 half spaces. All right, and again, depending on the problem, you may view it as an intersection of half spaces, or you may want to view it as a convex combination of the convex hull of some finite set of points. Okay, so just to see why this may be important, let's look at an example. Okay, so we look at another problem which I call max weight matching on a complete bipartite graph. So the problem is the following. Okay, you have n people. I mean, this goes under various names. Max weight matching. It's also belongs to a class of problems called stable marriage problem, and so on. So one way to think of it is the following. So you have, let's say, let's say you have n boys and n girls, right? Or if you want to view it in a different way, let's say that there are n students and n advisors, and your goal is to allocate students to advisors, right? And right, so the goal is to ensure that each student gets allocated to exactly one advisor, and each advisor is let's say advising only one student at a time. Okay, that's a problem. Okay, but now where does optimization come into the picture at all? Okay? So let's say that each student gives a particular preference, right? I'm pretty sure that in your when you were opting for advisors, at least the master students, you would have given a certain preference, right? So let's try to solve that problem itself. So each student can give a preference for a particular advisor. Let's say that it's any positive real number between 0 and something. We don't really care what the numbers are, but essentially it's a ranking, right? So each student ranks the advisors. So for the first student, for each of the advisor gives a particular ranking. Now, basically, it's just a bunch of numbers, right? So let's say that for advisor 1, it is, say, 0.3, advisor 2, it is, say, 2, advisor 3, it is, let's say, 1.2, for advisor 4, it is, say, 0.22, something. The numbers don't really matter, the absolute values of the numbers. At least for this purpose, we don't care what they are. Maybe they could be integers, for all we care. And this is done by each student. Okay, and the goal is to somehow come up with this allocation. So that, let's say, the total weights, right? So corresponding to each edge, there is a particular weight, right? Or each student advisor allocation, there is a particular weight, and you want to ensure that now corresponding to one particular allocation, you can define the weight of that particular allocation. So for example, let's take three students and 3 advisors. Right, let's say let's say this is 3, 2, 1, and this is, let's say, 1, 2, 3, and this is 2, 3, 1. Okay, these are the preferences given by each student for each advisor. All right, and you choose one particular allocation. Let us say the one allocation is 1, 1. One allocation is just 1 maps to 1, 2 maps to 2, and 3 maps to 3. Okay, what would be the total weight of this allocation? It would just be 3 plus 2 plus 1. Okay? The sum of the edges which are ultimately selected in this matching, as I call it. So what is a matching? A matching is just this basic allocation, an allocation which satisfies the property that every student is allocated to exactly one advisor and every advisor is allocated to exactly one student. Okay? That's what we call a matching. So the weight of this particular matching would be 3 plus 2 plus 1, which is 6. But is this the maximum weight matching?
We want the minimum weight.
Oh, okay. So here the preference is so it's not 1 is the highest preference, 3 is the highest preference. yeah, so maybe I shouldn't have used the word ranking, but sort of a score.
It just has a much higher weight than that has to be part of the final graph, final set.
What do you mean?
So, for example, if say the edge from 3 to 3 had something like 100, a weight of 100,
Correct.
then no matter what the other edges would be, that would have to be included in the optimal solution.
Depends, right? It depends on what the others can give.
Yeah, those are much lower. Those
Okay.
are the same scale around 1 to 9.
Okay, yeah.
In that case, the optimal solution will have to have that edge.
Correct. That's true. That is true. So generally there are constraints on what you can give, right? For example, you can't say that one person gives 100, 0, 0, and the rest of them give, say, 1, 2, 3, and so on. That would be sort of unfair in some sense. So we're not concerned about that. Let's assume that this is presented before you, okay, somehow. So we're not going to worry about how these scores were given, but given the set of scores, yeah, because for example, even advisor matching for that matter is not as straightforward as just solving a maximum weight matching problem, right? But now, so that's the weight of this particular matching. For this particular matching that I have written over here, the weight is equal to 3 plus 2 plus 1 equal to 6. So just by looking at this, can you guess what the maximum weight matching should be? 9. And what is the allocation? 1, 1, 2, 3, and 3, 2. Right? Does everyone agree? Okay. Now we have this particular problem. How do we formally state this problem? Ultimately we want to formulate this as a mathematical optimization problem. So what is the optimization problem? How do you describe this?
One question would be that given a matrix that has all the relations.
Okay, so let's say that as part of the problem description, you are given the following n by n matrix. Right, so let's say that I call this matrix W, which is an n by n matrix, and Wij is, let's say, the score given by I about J. Okay, so in that particular 3 by 3 example, the weight matrix would be 3 to 1, 1 to 3, 2, 3, 1. Correct? So this would be my weight matrix. So this is specified to you. Correct? Now ultimately our goal is to generate a matching. Correct? And as you rightly pointed out, matching effectively corresponds to a permutation. Right? So it's just a permutation of 1 to 3 up to n. Right? That describes the matching. But in terms of this graph that I drew over here, a matching is basically just it's another subgraph of this particular graph. So I had a complete graph with weights on the edges. I'm looking at a subgraph with certain properties that every vertex on the left is connected to exactly one vertex on the right, and every vertex on the right is connected to exactly one vertex on the left. Correct? Okay, and we want to make sure that we want to maximize the sum of the edge weights in the final generated permutation or the matching. Correct. So all right, so in that case, let us say that. So now, firstly, we need variables, right? Now, how do we choose our variables? One way to say is that my variables are basically permutations. But that leads to a problem. Permutations are, well, I have n factorial many permutations. I don't get a continuous parameter optimization problem. I can, of course, solve the problem by just running through all possible permutation, computing the weights for each permutation and finding the permutation which maximizes this. Right? It seems doable, but let's say that n is, say, 1,000. Right? It's impractical to even compute the weights for all possible permutations. Yeah.
Treated as the kind of a convex solve problem, and optimal solution will get one of the vertices.
Correct. That's what we'll head to. Right. So we'll still formulate it as a continuous parameter optimization problem, but we'll use that basic property that we had, that if you have a linear, again, if it's a linear program, then the optimum is always going to be a point on the vertex. It's going to be a vertex. Right? But that we'll come to that just a little bit later. Let's first formulate it as a discrete optimization problem itself, right? And then we look at a relaxation. So, well, the variables, again, you could take this to be the set of all possible permutations, but I'll choose it a little differently. So I'll say that my variable is going to be another matrix. Okay, it's going to be an n by n matrix, right? Which basically is going to give me the connectivity of the final matching that I have chosen. Right? So in other words, xij is 1 if I is allotted to j. So each xij is either 0 or 1. Okay, that's what we want. This is not sufficient. We want to ensure that each student I is allotted to exactly one advisor, and each advisor is advising exactly one student. Right? How do you formulate that as a constraint? Yeah. So basically, you look at the matrix X. The row sum for each row should be equal to 1. The column sum for each column should be equal to 1. Agree? Right? Because the row sum for any row gives you the number of advisors allotted to that particular student. Remember, the rows are indexed by the students, the columns are indexed by the advisors. So the row sum gives you how many students are allotted to this particular advisor, and the column sum gives you the row sum gives you the number of advisors allotted to that particular student, and the column sum gives you the number of students allotted to that particular advisor. All right. So in other words, you want summation overall j xij should be equal to 1 for all I, and summation overall I xij should be equal to 1 for all j. So these are constraints. Okay, so now what is the optimization? What is the objective? Okay, yeah, so the inner product between x and w, or basically take the element wise product and then sum. Objective is basically summation over all I comma j wij xij. All right. Yeah. The goal is to maximize this. Overall x which satisfy those constraints. Capital X. Right? Any questions up to this point? So once again, we have a nice linear program, right? The objective function is linear in the variables. The constraints, at least these two constraints, are linear in the variables, but this is not, right? I'm saying xij is either 0 or 1. But instead, what can I do? I can instead say that xij can take any value between 0 and 1. That's an explicit thing that I can do. I can relax the problem and then hope that I'm going to get a solution which is which satisfies all the I'm going to get the same solution as though I did not constrain this to be in 0, 1, right? Right, this is a relaxation that I'm choosing to make. Now these are two different problems. Right, in the first case it was an integer program because xij's could only take integer values, in fact just binary values. But now I'm saying that xij can take any real number between 0 and 1. Now this is a linear program, right? And as we've seen before, or at least as I've stated before, the minimum, the max, the optimizer is going to be a vertex. But how do I know what all vertices are there? Right? This is not the unit cube, right? I'm also imposing some additional constraints over here. Correct. So if I had only these constraints, then that corresponds to the unit cube. But now I'm imposing additional constraints. So the vertices now of the polytope, the constraint polytope, are not going to be the vertices of the unit cube. They could be something very different. It's going to lie within the unit cube certainly, but I could potentially have generated fractional vertices. Right? Do you see the problem? Right? So for example, let's just take a 2x2 case, not this problem, but have x comma y, and these are the vertices of the unit cube, right? So this is 0, 0, 0, 1, 1, 1, and 1, 0. Right? I want to basically solve some optimization problem basically on the vertices. Correct? Now I impose certain constraints, right? Certain linear constraints. Maybe the constraints are defined by the following planes, right? The following lines, which look like this. All right. So my new constraint polytope would basically be these points, this region. Correct? But now I've retained two of the original integral points, right? 0, 0 and 1, 1. But because of these constraints, my constraint polytope is such that there are two fractional vertices. So suppose I solved this linear optimization problem. I used the solver to solve this, and ultimately it said that the optimum value is achieved at this particular vertex. Now this is a fractional vertex, and it doesn't give me a solution where xij is 0 or 1. Correct? Do you get the problem over here? Right? I had an original problem where my xij's had to be either 0 or 1. I've relaxed this problem to the case where xij can take any number, fractional number between 0 and 1. So I get a linear programming problem. I solve the linear programming problem. I solve the linear program. I know that the linear program is going to give, it has an optimum point at one of the vertices of the constraint polytope. The constraint polytope could potentially look something like this.
Second, be the integral point with all the vertices.
Why?
Like, because we have this constraint that if the row sum and column sum should be less than or equal to 1.
Okay, so
I don't know how to explain this rigorously, but like,
Yes.
intuitively, one of the fractional points was the vertex.
okay,
Like, if I kept extending it a bit, like as in like got to like the integral point, technically that should also be a valid point, but if this was a vertex that would lie outside, right?
yeah, but you should be, I mean, that may not always hold, right? How do you even visualize such a polytope?
Example, 1, 0 should also be a part of your polytope, like because it would have that.
If it had these particular constraints, fine. 2 by 2 case, it's simple. Right? But in general, in n dimensions, it's not very easy to visualize this. Now, in this particular case, for this particular problem, it turns out that the vertices of this particular polytope indeed happen to be integral. Right? And in fact, they turn out to be the set of all permutation matrices. Right? So this particular polytope. So let's look at any matrix X where xij is in 0 to 1 and the row sums and column sums are equal to 1. Right, so any matrix which satisfies these constraints is called a doubly stochastic matrix. All right. So doubly stochastic matrices arise in a number of applications, most particularly when you deal with Markov chains. Right. So if you have any stochastic matrix, for example, if just the rows sum to 1, then you can view this as sort of a one-step probability distribution. Right? What is a probability that say the next point is going to be I, given that that you're currently sitting at G. Right? And a doubly stochastic matrix is a special case of a stochastic matrix. One which is in some sense you can go the reverse way as well. Whatever. Let's not worry about where doubly stochastic matrices come from, but this is what is called a doubly stochastic. Right? And if the xij's can be only 0 or 1, then that essentially corresponds to permutation matrix. Right? If xij right? Now, if I take a convex combination of permutation matrices, what can you say?
Or combination.
It's okay. Is it going to be doubly stochastic? To be more precise, right? So, if you look at, yeah, sorry, which one? It's not a joint distribution. It's really a conditional distribution. So if it had to be a joint distribution, the sum of all entries should be equal to 1. But here it's only each row and each column sum to 1. So that's what. If only the rows sum to 1, then it basically corresponds to a conditional distribution. Or if only the columns sum to 1, this is a special distribution. Right? So any convex combination of permutation matrices is doubly stochastic. Right? But what is not easy to see, although I don't know, it may seem intuitive, is that any doubly stochastic matrix can be written as the convex combination of permutation matrices. It is a fairly deep result. It's called the Birkhoff-von Neumann theorem. So the set of all doubly stochastic matrices it's a polytope, and it's called the Birkhoff polytope. And this theorem says that the Birkhoff polytope is basically the convex hull of the set of all permutation matrices. Right? I'm not going to prove this, but it's not very hard. The proof is not very difficult, but it's very clever. It's a beautiful proof. It's just probably a 5-6 line proof. You can look it up online. But this is one of those deep results which can be proved pretty straightforward. Right? Once you see the proof, you see, it's obvious, but it's not easy to just come up with a proof. All right? Yeah.
So these permutation matrices,
Correct.
each of them are going to be like a base vector for the n by n space. Right? So we consider them each of them as
They're basis vectors, yes, but again, we're not looking at the vector space, right? We're looking at the convex hull. So in this case, these are going to be the vertices of the Birkhoff polytope.
Element wise, the convex combination, the element wise for the matrix, right? So each of the elements.
Sorry?
When we say the convex combination of the matrices, we basically mean convex combination of each individual elements, right?
Yes.
In that case, if the element is between 0 and 1,
Yes.
and we have alpha between 0 and 1,
Yes.
isn't it obvious that the element will also be between 0 and 1?
It will be between 0 and 1, yes. Again, the convex hull of the permutation matrices is going to be within the Birkhoff polytope. That is fairly straightforward. But it's not too straightforward to show that the Birkhoff polytope is equal to this. right? It may seem intuitive, but there can be other cases where this intuition itself doesn't hold. It may seem that that is the case, but that's not true. Right? It's not all valid conditional distributions, right? It has to be doubly stochastic. Correct. Okay, so maybe I don't want to elaborate too much on this, but perhaps later, sometime offline, I'll give you another example of something which looks as though okay, so in fact, you can also look at the case. You can do all of this for the case where the number of vertices on the left and the right are not the same, right? Similarly, you don't have permutation matrices, but there's still a notion of a matching, right? So in this case, it's not true that that polytope is generated only by integral points. In some cases, you can have fractional vertices, and that's not straightforward. Yeah, again, I don't want to spend too much time because we'll be digressing at this point, but I will provide an example where you can have fractional vertices as well, right? I mean, it may seem as though there can't be any fractional vertices, but in fact there are. Okay, so at least in this case, what does it mean? It means that if I solve the linear program with this relaxation, this relaxed linear program, then the solution that I get will be a perfect match. Right? So if I had to solve this particular problem, I might as well relax this to x being between 0 and 1, instead of saying that x has to be either 0 or 1. All right. And again, it's fairly simple to just solve this. You can just use something like CVXPy, set up the problem, and get the max weight matching. Right. So right, so let's say I take W equal to the same matrix that I had. Can you just tell me what the matrix was? Yeah. 3, 2, 1. 1, 2, 3. 2, 3, 1. Right, and okay, tell me how would I code this up? So x I have to first define my variables. So how do I declare a variable? It's cp dot variable f 3, 3. Right, my variable is basically a 3 by 3 matrix. I have to define my constraints. And what are the constraints that I have? X, of course, should be between 0 and 1. You can just say x greater than or equal to 0. And what else do I want? X less than or equal to 1. But in fact, when I say that the row sum has to be equal to 1, that automatically ensures that each xij has to be less than or equal to 1. Right? So all I need to just specify is a non-negativity constraint. What else? The sum along each axis should be equal to 1. So Cp dot sum of x comma axis equal to 0 should be 1. Yeah, any issues? Fine. I mean, I could as well do Cp dot sum of x axis equal to 1 is equal to 0. Okay, what's my objective? I need to do sum of so I do element wise product of W and X and sum all the entries. I just set it up as Cp dot right. So I just use CP exploit, run this, and is it the same as what we had earlier? So 1 gets mapped to 1, 2 gets mapped to 3, and 3 gets mapped to 2. So, I mean, this was a simple case that we could very easily solve. But for example, if I had, let's say, 100 vertices on the left and 100 vertices on the right, and some complicated looking weight matrix, I could still do this just as easily as I did here, right? So, for example, I could just take I could potentially take a random n by n matrix uh, I of course can't, no point in printing this, but that's it, right? It's that quick. And if I had to see what these look like, of course, printing them out would not be particularly helpful, but I can at least visualize this. Let's say what the W matrix looks like. Here's sort of a visual representation. So darker values would be values which are close to 0, and lighter values close to 1, right? It's a completely random matrix. And what does my solution look like? Right, I get permutation matrix. Right, so sorry, yeah. Above this. Okay, so W is basically the weight matrix. So W is the weight matrix. Basically, what is the score given by user I about object J? Right? Okay, yeah, the way I generated this is using nb.random. So each of them is IID chosen between 0 and 1. Right? The same thing, I didn't change anything else. And this is what the weight matrix looks like visually. And this is what the solution looks like visually. All right? Any questions? Right, so again, CVXPy is a very useful tool because you can just using a few lines of code, you can solve something as complicated as this. Now, this is not the most optimal way to solve this particular problem. Even this particular problem, right, of maximum weight matching. There's been a lot of development in this particular area for like several years, maybe around 1 or 2 decades ago. One way is, of course, to solve the linear program, but there's also a graphical way using what is called belief propagation, and that has lower complexity than actually solving the linear program itself. Right, so there are better ways to solve this particular problem, but as long as you're not too focused on the computational complexity, linear programming is one easy way to do it. Right? Great. So now we have some understanding of what polytopes look like, and what are the consequences of those when it comes to solving linear programming problems, right? So, but ultimately, what did we do? We use this sort of toolbox, which is CVXPy, to solve problems. But how does CVXPy basically work? Let's just maybe peek under the hood. When I give certain kinds of constraints, we saw that it throws up errors, right? Unless the constraint set is convex and you're trying to minimize it. So all it can do is solve minimization problems for convex functions and maximization problems for concave functions. If I give a convex function and try to maximize it, it will immediately throw up an error. Similarly, if I give a concave function and try to minimize this concave function subject to constraints, it will throw up an error. It will not try to solve for it. So what is CVXPy really doing? It's actually checking for certain rules, right? Because it's not easy to just determine whether the function is convex or not, whether the sets are convex or not, right? So these guys, they've developed what they call disciplined convex programming, which is kind of a set of rules. So you have some of these basic constraints and basic functions. And what do? You sort of compose all of these together. Right? So you can express certain functions as sum of squares. Now, just x square itself, what is it? It's a convex function. Right? So sum of squares also happens to be convex, as we'll see later. Similarly, the constraints, right? Now you don't have just one constraint, but a composition of various constraints. If each constraint is convex, then imposition of multiple constraints is like taking the intersection of multiple convex sets, and that happens to be convex. Right? So we'll see these various properties of convex sets and convex functions, which essentially let you design such rules for checking whether a given problem is actually a convex optimization problem or not. Right? Again, it does not include all possible convex optimization problems, because there could be some weird convex function that you've never seen before and you can't very easily describe in terms of more elementary functions. But as long as you can somehow describe it in terms of these elementary functions, you can determine whether you have a convex function or not, or whether you have a convex constraint set or not. Right? So we'll first see some of these basic sets which we know are going to be convex or not, and then see that if we perform some operations, let's say I take a transformation of a certain set. If I take a transformation of a certain convex set, is the transformed set going to be convex or not? All right. So far we've seen a bunch of sets. So one is an affine set, what are convex sets. We've seen hyperplanes and polytopes. Right. So what about a hyperplane? Is a hyperplane convex? Yes? Yes? No? How many say yes? Up high? How many say no? Some of you didn't raise your hands. So it is convex, right? And what about half spaces? Are half spaces convex? Are half spaces convex? Are half spaces convex?
Yes.
I can't hear. Okay, that's better. All right. So now, what about a ball? Right? How do we define a ball? So a ball in n dimensions, center, let's say xc, and radius r. How do you define this? Let's take the standard Euclidean ball. How do you mathematically define a ball of radius r with center at xc? Norm of what?
X.
So
X minus X.
it's the set of all points x in Rn such that the norm of x minus xc is less than or equal to r. So this is the closed ball of radius r with center xc. Now in principle, I need not necessarily use the Euclidean or the 2 norm. I could potentially use any other norm and it's still going to give me a norm ball. Geometrically it's going to look a bit different, but in any case I claim that this is going to be a convex set. Why is that true?
We can draw a line between any two.
Okay, that's geometrically that's true. But suppose I have to prove that the norm ball is convex. Yeah. Okay, so let's just take 2 points. Let's take x1, x2 in this ball. I have to show that for every alpha between 0 and 1, alpha x1 plus 1 minus alpha x2 is also in the ball. Right? What does that amount to showing? I have to show the norm of this minus xc is less than or equal to r. But what is this equal to? I can write xc as alpha xc plus 1 minus alpha xc, right? Because alpha is some number between 0 and 1. So this is alpha times x1 minus xc plus 1 minus alpha times x2 minus xc.
Okay, use the triangle.
Correct. Now I can just use triangle inequality. So this is alpha times x1 minus xc plus norm of 1 minus alpha times x2 minus xc. And this is something that every norm should satisfy, not just the Euclidean norm. Right? Next. Correct. So that's correct. But yeah, so one step before that is that another property of the norm. So any norm should satisfy triangle inequality, but it should also satisfy the scaling property that the norm of alpha times some vector is equal to alpha times the norm of the vector. So this is alpha times norm x1 minus xc plus 1 minus alpha times norm of x2 minus xc, but each of these two is less than or equal to r. So this is less than or equal to alpha r plus 1 minus alpha. Right? So it's a convex set. Correct? Now, just as we defined a ball, which is sort of the generalization of the circle to higher dimensions, we can also define an ellipsoid, right, which is a generalization of the ellipse. And how do we define this? It's basically just an affine or a linear transformation of a ball. You can think of this as the set of all x such that is less than or equal to some. A more sort of general way and sometimes a more useful way of looking at this is in the following manner. So it's a set of all x such that x minus xc transpose A transpose A, x minus xc is less than or equal to r square. Now, again, since A can be anything in general, I'll take this to be less than or equal to 1. Because scaling this by 1 by r is the same as scaling this matrix A by 1 by r. Right? So any ellipse or any ellipsoid can be represented in this particular form. And in fact, I'll take a slightly more general definition of an ellipse. So an ellipse is the set of all points such that xc transpose P is less than or equal to 1 for a positive definite matrix P.
So the A transpose A always positive.
So A transpose A is symmetric. We agree? And is it positive definite? Is it positive semi-definite? how do you show whether it's positive semi-definite or not? Just take X transpose A transpose A X. This is just norm AX squared. So it should be greater than or equal to 0. Right? So A transpose A is a symmetric positive semi-definite matrix. We typically constrain P to be symmetric positive definite. So typically you take A in this case to be a full rank matrix. If A is full rank, then A transpose A is going to be positive definite. Right? Okay. So maybe let's stop here. Yeah, any questions? Okay.